Right. Um, I'm Alex Walker, and I'm going to talk to you about the CryoCube project from Sierra Lobo. Let's see, a little bit my agenda. I'm going to give a corporate overview of Sierra Lobo, then talk about the CryoCube, uh, and give a give an overview of the mission, the scope of the project, some of the thermal analysis that we did, and uh, basically a little bit about the attitude determination control subsystem. So Sierra Lobo is basically divided into three parts. We have our support service contract business, we have our engineered systems business, and we have our internal research and development. The CryoCube falls under the internal research and development, so I'll focus on that. Um, our engineered systems group and IR&D are at our Technology Development and Engineering Center complex, or TDEC. Um, Basically, we can provide cradle-to-grave services at this complex. We have IT, infrastructure, and virtual engineering. We have manufacturing and assembly capabilities, a class 10,000 clean room, research lab with bonded storage adjacent. Um, and yeah, our main focus is cryogenic systems. So we have a cryogenic test facility, or Sierra Lobo test facility, as we call it, SLTF, which is that building in the bottom right. It's got a 1,500 gallon LH2 storage capability, and it's got all the electrical classifications that allow us to do uh, liquid hydrogen and liquid oxygen tests. um, so our primary skills and capabilities, we have research and development, design, simulation, analysis, solid modeling. We can manufacture systems. Um, we can manufacture pressurized systems using piping, tubing, valve, integrate systems. Um, we have over 35,000 square feet of engineering and manufacturing facility. Um, we have liquid hydrogen test capability, as you saw on the previous slide. Our technology interests include underwater vehicle and energy systems, our cryo tracker, mass gauging system, which can track the liquid level and temperature of cryogenic liquids in storage tanks. We have cryogenic storage systems, and we also specialize in densified propellant management systems and cryocoolers. These applications include launch vehicles, missiles, spacecraft, cryogenic fluid management, uh, ground vehicle energy systems using liquid hydrogen, liquid oxygen. Also have applications in ground support equipment. Some of the larger test facilities in NASA Glenn, for example, um, we we have capability to support them. Um, we can support medical industry, laboratory and test facility, um, among others. To date, our company has invested more than $30 million in contract work, more than $2 million in internal research and development, with such partners as Air Force, Navy, NASA, DoD. There's just a few of our projects that we've worked on over the 20 years of our company's existence. Getting more into the CryoCube specific technologies that we have our reduced gravity cryo tracker system, which is a lightweight, low power sensor that's designed to detect liquid vapor interface and the temperature of the liquid and the vapor of cryogen in a cryogenic tank in a low gravity environment. Um, it can be used in slosh type environments to validate CFD models. Um, we have so far validated this reduced gravity cryo tracker in the Vomit Comet using liquid water. And we've also validated the technology in 1G using liquid water and liquid nitrogen. Here's basically a picture of CryoCube. So the CryoCube is a free-flying spacecraft based on the 3U CubeSat form factor with modular design that can accommodate different payloads. Basically, the payload is the last U and about U and a half um, that can get down to cryogenic temperatures. This can support cryogenic experiments that you can't really put on the ISS due to restrictions in use of cryogenic liquids like liquid oxygen, liquid hydrogen. The CryoCube can get down to about 100 Kelvin with just passive thermal techniques and about 30 Kelvin using active cooling. So possible payloads include cryofluid management payloads, sensors such as the cryotracker sensor, validation, um, imaging, basically the liquid vapor interface, etc. The first CryoCube is actually uh, done with a partnership between Sierra Lobo and NASA Kennedy Space Center. And it's being manifested on a flight next year through the CubeSat launch initiative. So a little bit about the first CryoCube mission. We're going to demonstrate our cryogenic fluid management technology, the cryotracker, and collect data on the cryogenic fluid phenomena and microgravity. Basically, we're going to image the liquid vapor interface in our tank in the last U. We're going to demonstrate our thermal management capabilities aboard a CubeSat, quantify the effect of non-condensable gas on tank pressure during the thermal cycling that we expect to get with the passive thermal control. And we're going to, above all, determine the performance of our reduced gravity cryo tracker in microgravity and increase our TRL of our technology. Cryo tracker, or the CryoCube 1, is scheduled for delivery for acceptance testing in April 2014 and will be launched in December 2014 on an Atlas V. We're going to ride on the aft bulkhead carrier. A little bit more on the scope. We're going to reach a temperature somewhere between 80 to 110 Kelvin, where we were shooting for less than 120 Kelvin. We're going to produce oxygen gas aboard the CubeSat and condense it into a liquid. And we're going to also record the temperature and liquid levels. To do so, we're going to use a CubeSat form factor. We're going to use a deployable sun shield / solar array and an earth shield to help us get down to cryogenic temperatures. We nominally are going to use a solid source oxygen gas generator. We're going to also use a camera for remote from the experiment to image the liquid vapor interface and to actually allow the camera to function because it can't function at the cryogenic temperatures. We're using the NASA ground-based network, and we're using commercial off-the-shelf components when practicable. We have an orbit that's 700 by about 400 kilometers. Our inclination is 55 to 60 degrees, and we're using basically the average altitude for all our initial calculations. So there were nice pictures that went with these. We were considering two configurations. One would have been a sun pointing, nadir pointing during sun pointing during non-eclipse, and nadir pointing during eclipse. And the second would basically be an optimization of our Earth pointing, sun pointing angle to achieve the best thermal environment. We went with the second configuration because it's a less demanding attitude control problem. And we need all the space that we can get for our actual experiment. So we didn't really have the room for you know, CMGs or um, you know, anything more that would allow for better pointing. Basically, for our thermal requirements, we want a 10-degree pointing accuracy. We decided magnet torquers to save space and power. And we're using a proportional derivative gain scheduled feedback to apply the appropriate control, which is basically a magnetic moment. And we're going to use a fuzzy logic system to provide gain scheduling, and the controller was tuned using a genetic algorithm. Basically, here's the yeah, that's just the difference in the PowerPoint versions that were used. We're using a typical proportional derivative feedback controller, using a quaternion as a proportional term. The angular velocity is the derivative term. And we're gain scheduling using a fuzzy logic controller, which fuzzy logic is basically a function approximator. Can approximate any function to any degree of accuracy. So it sort of works well as a gain scheduler for this application. Yeah. And like I said, we used a genetic algorithm to tune our fuzzy gain scheduler. Genetic algorithm is basically a heuristic optimization method based on the survival of the fittest. Our potential solutions were parameterized and then put through this algorithm to find the most optimal as defined by our cost function. Solution, we used a genetic operations of crossover. We used 2-point crossover and a mutation operation. We used a 70% population generated from the crossover operation and 30% population generated by mutation operation. Basically, use a high mutation rate in order to ensure that our solution would not converge to a local minimum. We also coupled this with elitist selection in order to really hone in on good solutions, so we didn't diverge from any solutions as well. Yeah, and below you can see our cost function that we use to optimize our gain scheduling. With the gain scheduled controller, you can see we hit our requirements, better than 10-degree pointing accuracy over the duration of the mission, and that's with an initial 60-degree angular error offset and some initial angular angular velocity, typical after a detumble phase with magnetic actuators. And I guess I'll speak just a little bit about our state estimation. We're using a two-vector algorithm, extend the Kalman filter, and we're using gyroscopes, sun sensors, and magnetometer. So like I said, we're going to achieve an 80 to 110 Kelvin temperature. We got gain scheduled attitude control, magnetic attitude control that's going to get us to within our 10-degree pointing accuracy. The thermal requirements require, and we're currently assembling and testing our engineering development unit, and CryoCube will be ready for test in April 2014 and flight in December 2014.
Thank you very much.
Yep.